me share my screen.
Mhm.
I hope you can see it.
Yes, we can see it.
Perfect. Today we are going to explore probabilistic aspects in machine learning, which help us make sense of uncertainty in our data and models. And throughout this lecture, we will go over the basic concept and highlight key points in model building. By the way, image was generated by the DALL-E model with the prompt based on the title of today's lecture. Actually, this is how the model envisions our topic. We frequently hear the terms data science, artificial intelligence, and of course, they have become integral to almost every aspect of our lives. Whether we are searching for a movie on Netflix, scrolling through social media, or using voice assistants like Siri or Alexa, AI-powered algorithms are at work behind the scenes. They analyze our preferences and provide some personalized recommendations and making our experience seamless. AI also plays a role in areas like fraud detection in banking, where machine learning algorithms help ensure the safety and reliability of financial transactions. Although they are widely used, distinguish between concepts like big data, data science, machine learning, deep learning, and artificial intelligence can be challenging at first. Each of these areas has its own purpose, but they also have overlapping components, which is why I've constructed this table to understand their relationships better. So let's delve into each of components to clarify their distinctions and their specific functions. At the core, all these concepts are connected and layered within each other. Big data form the foundation. It refers to enormous volumes of data generated from diverse sources. For example, social media, Internet of Things devices, transactions, and more. These data sets are so large that they require specialized tools like Hadoop and Spark for storage and processing. Data science is built upon big data and involves analyzing the visualizing data to extract actionable insights. And data scientists use a combination of statistical model and computational tools to understand patterns, correlations, and trends in data. Tools like Pandas and NumPy are widely used um, to manipulate data, while visualization libraries help in making these insights more comprehensible. Machine learning is a subset of data science that focuses on developing algorithms that learn from data without explicit programming. ML leverages insights derived from data science to make predictions or decisions. Techniques like linear regression or supervector machine are commonly used, along with libraries such as scikit-learn. And machine learning algorithms continuously improve as they are exposed to more data, allowing them to refine their predictions over time. Deep learning is a specialized branch of machine learning that uses multi-layered neural networks to model complex patterns in large data sets. And unlike traditional ML methods, deep learning methods like convolutional neural network or transformers are capable of uncovering more abstract relationships. DL requires significant computing power and utilizes frameworks such as TensorFlow and PyTorch. Artificial intelligence is a comprehensive concept that encompasses all the above. AI aims to create systems that performs tasks typically requiring human intelligence, such as learning, reasoning, and problem solving. It leverages ML and DL to create intelligent agents, such as chatbot like ChatGPT or autonomous system like AlphaGo. AI is a broader goal, and machine learning and deep learning serve as a key approach to achieving it. All these concepts interconnected, where each component built on the previous one. Big data provides the raw material for data science, which extracts knowledge, allowing machine learning to develop predictive capabilities. Deep learning further enhance this with sophisticated neural networks and contributing to artificial intelligence, which aim to replicate human-like intelligence. And understanding how each fits within this and what distinct role each plays in this essential for grasping how they contribute to advancing technology. Let's consider the key idea of probabilistic modeling. Often, machine learning models assume that the data is generated from some probabilistic process. And the goal is to learn the underlying distribution to make accurate predictions or decisions. We start with our data set, represented by a set of input-output pairs. The inputs, denoted by xi, are vectors in d-dimensional space, while the outputs yi could either be real values for regression problem or discrete classes for classification tasks. And the goal or objective here is to learn model that approximate the relationship between our input x and output y. To achieve this, we need to consider a few important questions. First, what methods can we use to effectively approximate this relationship? And second, how do we ensure that our model captures both the patterns and the variability in the data? And the third, what metrics should we use to evaluate the model's effectiveness in capturing the true relationship between X and Y? During our lecture, we will find answers to these questions. Let's consider three main types of machine learning: supervised, unsupervised, and reinforcement learning. In supervised learning, we learn from labeled data, mapping inputs to outputs. Examples include, for example, regression for predicting house prices and classification for recognizing handwritten digits. In unsupervised learning, there are no labeled output. We aim to find patterns such as clustering customers by behavior or reducing dimensional for visualization. And finally, reinforcement learning is about learning a policy to maximize the total rewards in an environment, such as training a game agent. Each type serves a unique purpose depending on the data and the problem at hand. Today, we will focus specifically on supervised learning, which in turn addresses issues of regression and classification. Regression is a fundamental supervised learning technique. And its goal is to predict a continuous target variable based on input features. And the objective in regression is to learn a function f of x and theta that maps the input x to the output y by minimizing the prediction error.
I'm sorry to interrupt you because we cannot see your right part of the screen. Maybe you can.
Okay, that's a little bit strange.
Okay, so this is better.
Okay, I'm sorry, maybe we can, yeah.
Okay.
It was okay in the previous slide?
The previous one was okay.
Okay, I see. Thank you. Yes. So the model we are considering is a linear function of the input features. Here, theta represent the parameters we want to adjust to find the best fit. And the goal is to minimize the error between the model's predicted output and the actual output. And to achieve this, we often use mean squared error. The formula for MSE, the sum of the square difference between the actual values and the corresponding values predicted by the model. And we want to minimize this value to make it as closer to zero as possible, which means our predictions are becoming more accurate. And this image represents a simple linear regression model. The blue points represent the data points observed in the data set, and the line running through these points is called the line of regression. Just the simple example. As you see, this line attempts to best fit the data points by minimizing the distance between the points and the line, effectively showing the relationship between the independent and dependent variables. And here a couple of examples of regression in action. If we want predicting, if we have predicting house prices, based on different features of the house, such as size, location, and number of rooms, we can use linear regression. And more detail about this example are provided below. The sample example is predicting the temperature for the next day using weather data. We can use previous weather patterns, humidity, and other factors to estimate the temperature for the following day. Next, we will examine classification more thoroughly. Classification like regression, I can change the scale, is a supervised learning method. And however, in classification, we predict a discrete label rather than a continuous value. And the model estimates the probability of different classes based on input features and select the most likely one. The objective here is to learn a function f of x and theta that maps to the input x to a set of class probabilities and outputs the most likely class. And the model we use is f of x and theta equals argmax over a k of probability of label y equals k given features x equal x small. This means that we choose the class k that had the highest probability given the input x. And our goal in classification is to reduce the error between the predicted class and the actual class by adjusting the parameters, which are represented by theta. The formula here represents the empirical probability that the predicted class is not equal to the actual class. And we want to minimize this value to make it as closer to zero as possible, which means our predictions are becoming more accurate. And this image here illustrates two types of classification problem. Okay. On the left, we see a binary classification scenario where data points are divided into two classes, represented by green circles and red stars, separated by a decision boundary. On the right, the multi-class classification example shows data divided into three classes: green circles, red stars, and blue triangles. And in this case, multiply decision boundaries used to separate the different classes, highlighting the complexity of distinguish between more than two categories. Now we will cover some essential components in machine learning that deal with probability distributions. First, P of X and Y represent the joint distribution of the variables X and Y, describing how they occur together. This joint distribution can be broken down using the rule of probability, which gives us probability of X and Y equals probability of Y given X times probability of X. Here, probability of X represent the marginal distribution of the inputs X. It tells us how often different values of X occurs in the data set. Next, probability of Y given X represent the conditional distribution of the output Y and given a particular value of the input X. This tells us about the relationship between X and Y, showing how Y changes when we know the value of X. A helpful way to think about this is that probability of X describe the variety of inputs we might observe, and the probability of Y given X tell us how the output changes based on these inputs. We will go through some examples of how probability distributions are used in machine learning. For regression problems, the output Y given X often follows a normal distribution. We denote this by saying Y given X follows a normal distribution with a mean given by a function of X and a variance sigma squared. Here, the function of X represents the expected value of Y given X, and sigma squared represent the noise or uncertainty in our prediction. For classification problems, we often use a softmax function. Softmax function to model the probability of Y given X. This function takes the exponential of the weighted sum of the input X and adds a bias term, ensuring that all the probabilities for each class sum to 1. In this equation, WK and BK are parameters for class K. And the key idea is that the joint distribution of X and Y captures all the variability in the data, including both the patterns, which represents deterministic relationships, and the noise, which represents random variability. And understanding this joint distribution help us make prediction and quantify the uncertainty in our model. Now, let's take a look at this example of using linear regression for predicting house price based on different features. Again, the features denoted as xy. Xi are represented as vector in RD, where D is a number of features. And examples of this feature include the number of rooms, pollution index, for example, and the distance to the city center. The target variable denoted as yi represent the house price in thousands of dollars. And we use a linear regression model to approximate the relationship between these features and the price. The model is represented by h of x W and B, which equals the dot product of the weight vector W and the input X plus a bias term B. And to break down the variable further, X is the input vector of features. Again, such as room, pollutions, distance, so on. W is the weight vector that represents the importance of each feature. And B is the bias term, which accounts for the baseline price when all features are zero. H of X, W, and B is the predicted house price using this model. And Y represents the true house price. Our objective is to find the values of W and B that minimize the prediction error based on the training data. To consider this example, we need to introduce the concept of a loss function. A detailed discussion will be in the second lecture, but for now, it's enough to understand that a loss function is a specific function that shows us how far apart two values are. And the function takes only positive values, allowing us to sum the loss function across different points and get an overall assessment for all points. The sum and average of this loss function across all points are referred to as empirical risk, which will also be discussed in more detail in the second lecture. In this example, we will refer to it as to the cost function. The loss function used here is MSE. It used to measure the prediction error. The loss function denoted by L or Y and Y hat is given by the square of the difference between the true value Y and the predicted value Y hat. In this constant, Y represented again the true of the target variable, which is the actual house price, and Y hat is the predicted value, which we calculate using our model. This is represented as W transpose time X plus B, where WAB and B are the model parameters. Our optimization objective is to minimize the cost function J of W and B, which combines both empirical risk and this term we call regularization. The cost function is given by 1 over n times the summation for I from 1 to n of the square difference between yi and h of xi, w, and b plus lambda times arrow w. The first term measures the average prediction error across all training samples. And second part of the cost function is, again, regularization term, which helps prevent overfitting by penalizing large weight values, effectively controlling model complexity. And the regularization strives to control by the parameter lambda, which determines how much emphasis we place on keeping the weight small. In summary, our goal in linear regression is to learn the model parameters W and B that minimize the cost function, balancing both prediction accuracy and the model simplicity. The objective here is to find the optimal weights W and a bias B that minimize the cost function J. To do this, we use the gradient descent algo with the following steps. Step 1, we begin by initializing the parameters W and B either randomly or with the small values. Step 2, we compute the gradients of J with respect to W and B. Here, we simply take the derivative of the original cost function with respect to the corresponding variable. The gradient with respect to W is negative 2 over n times the summation for I from 1 to n of the difference between yi and x of xi wb, all multiplied by xi plus 2 lambda times w. The gradient with respect to b is negative 2 over n times the summation from I equals 1 to n of the difference between yi and h of xi, w, and b. Step 3, finally, we update the parameters iteratively using the computed gradients. The weight w at time t plus 1 is equal to the weight at time t minus the learning rate, denoted by eta, time the partial derivative of j with respect to w. Similarly, the bias b at the time t plus 1 is equal to b at the time t minus the learning rate, time the partial derivative of j with respect to b. The learning rate eta is a positive value that determines the step size for each iteration. Repeat this process until the cost function j of w and b converges, or the maximum number of iteration is reached. And again, w, the weights are adjusted in the direction of the negative gradient in order to reduce the error. B, the bias is updated in a similar manner, ensuring that the model's predictions align better with the target values. And eta, learning rate, control the step size. Is eta too large, the algorithm may not converge. On the other hand, if it's too small, the convergence process may be slow. The gradients partial g over partial w and partial j over partial b indicate the direction of steepest increase in the cost function j of w and b. And by moving in the opposite direction, the cost function decreases. And regularization lambda times prevent the weights from becoming excessively large, which help in reducing overfitting. And we have a stopping creation criterion, stop the iteration with the change in g of b and b, j of w and b becomes smaller than a predefined small tolerance value epsilon. And alternatively, stop after reaching a maximum number of iterations. Let's take a closer look at regularization, which is concept for improving the generalization of machine learning models. Regularization helps prevent overfitting, which occurs when a model learns not only the underlying patterns in the training data, but also the noise, leading to poor performance on new unseen data. And there are two main types of regularization, L2 rich and L1 less so. Here, the cost function consists of two components. The first term is the empirical risk, measuring the prediction error. And the second term is the regularization term, which adds penalty equal to the sum of the squares of the coefficients. And the parameter controls the strength of this penalty. L2 works by shrinking the coefficients toward zero, but it doesn't make them exactly zero, unlike L1. We can see it in the next slide. This helps in reducing the model's complexity without completely removing features, making it particularly useful in situation where we believe all the feature may contribute to the model, but their influence should be controlled. One of the primary benefits of L2 is that handles multi-collinearity effectively when features are highly correlated. In this case, L2 helps stabilize the coefficients by distinguish the effect among correlated features. Stabilize. So now that we've looked at L2 regularization, let's move on to L1 regularization, and we call it less so. L1 has its own unique properties, particularly in terms of enforcing sparsity. Unlike rich, less so can result in some coefficients becoming exactly zero. And by setting some coefficients to zero, L1 effectively performs like a feature selection, helping the model to focus on only the most significant features. This makes LESO particularly useful when we believe that only a few features are truly important for making accurate predictions. When should we use L1 regularization? Again, when we expect only a subset of features to be relevant to the model. And it's beneficial for reducing the dimensionality of the data, especially when we have a large number of features, and it can eliminate the less important one by setting the coefficients to zero. And the purpose of evaluation is to determine how well the model generalizes to new unseen data. We evaluate the model using a separate test dataset denoted as D. We will discuss this in more detail on the next slide. Here we can see metrics. And the first is, again, mean squared error, which we have seen earlier. It measures the average squared error of our predictions. And the second metric is the coefficient of determination, denoted as R squared. It's calculated as 1 minus the ratio of the residual sum of squares to the total sum of squares. In this case, the residual sum of squares is a summation of the square difference between yi and h of xiwb divided by the total sum of squares, which is a summation of the squares difference between yi and y bar. Here, y bar is the mean of the target values in the test dataset. R squared indicates how well our model's predictions match the variance in the actual data, with values closer to 1 indicating better fit. Now let's consider an important and fundamental concept in machine learning, data splitting. Why split the data? First, we split data to evaluate the model's ability to generalize to unseen data. We use the training data to learn the model parameters, such as weights and biases. And the test data is used to assess the model's performance on new, previously unseen examples. How to split the data? The data set is randomly divided into two parts, the training set and the test set. Typically, we use around 70 to 80 of the data for training and 20 to 30 for testing. It's important to ensure that the split is representative of the overall data distribution, so that both the training and test set are similar to the actual problem. And optionally, we may also use a validation set, which is an additional split to tune hyperparameters like regularization, strength denoted by lambda. Now, we will discuss the steps involved in splitting the data into training and test sets. First of all, shuffle the data set. It's necessary to avoid any ordering biases. This ensures that the data is randomly distributed and not influenced by the sequence in which it was collected. Then split the shuffle data. After shuffling, we split the data into a training set and a test set. The training set is used for fitting the model, and the test set is used to evaluate its performance. The number of training samples, denoted by n, is calculated as p times n, where p is the proportion of data used for training. For example, if p is equal to 0.8, then 80% of the data is used for training. When shuffling data for classification tasks, it's important to preserve class distribution to avoid skewing the data. This can be done using certified sampling. If the data set is small, it's a good idea to use cross-validation for better evaluation of performance. Cross-validation helps ensure that the model working across different subset of data. And here some of example. For house price prediction, we use 400 houses as a training set to fit weight W and bias B. And we use 100 houses at the test set to evaluate the mean square error and the R squared value. Again, this approach ensures that we can properly train the model and evaluate its performance on separate unseen data. Let's discuss overfitting in more detail. Overfitting occurs when a model learns not only the underlying patterns in the training data, but also the noise and the random fluctuations. This means the model fits the training data almost perfectly, but loses its ability to generalize to new unseen data. And as a result, it performs very well on the training set, but poorly on test or validation data. We have some indicators of overfitting. First of all, one of the clear indicators is when a model has high accuracy on the training data set, but much lower accuracy on validation. Another sign is when there is a large gap between training and validation errors. If the model performs significantly better on the training data compared to the validation data, it's likely overfitting. And how to avoid this problem? The use of regularization techniques and employing cross-validation. It's another important strategy which involves splitting the data into multiple folds to ensure that the model generalized well. And another effective approach is to reduce the model complexity or collect more training data, which helps ensure that the model doesn't learn specific details that are only relevant to the training data set. Let's now touch upon an important aspect of machine learning. It's cross-validation. Uh, it's a method for assessing how well a machine learning model can perform on new and seen data. And the idea, really simple, is to split the data set into multiple smaller training and validation parts to evaluate the model's generalization ability. In this example, we divide the data set into equal size groups called folds. Each fold is used one at a time as a validation set, while the rest are combined to form the training set. And this process is repeated for each fold, meaning every subset is used once for validation and multiplied times for training. This approach helps in evaluating the model's performance more comprehensively. And at the end of this process, we calculate the average of the performance metrics. Again, MSE or a square across all folds. This gives a more reliable measure of how well the model will generalize to new data and help us choose optimal settings, reducing the risk of overfitting. And this slide discusses some common variants of cross-validation, along with an example. And common variants is the next one, k-fold cross-validation. In this method, the dataset is split into k-folds, and the model is trained and tested k times. Each time, a different fold is used as a validation set, while the other are used for training. The second one, leave one out cross-validation. Here, each data point is used as a validation set exactly once, while the remaining points are used for training. This is essentially a special case where k equals the total number of data points in the dataset. The third option, stratified k-fold. This variation ensures that each fold preserves the same class distribution as the original dataset. It's particularly useful in classification tasks to prevent biases towards certain classes. And example, consider a dataset with 100 houses. And to perform a 5-fold cross-validation, we split the data into 5 folds, train the model on 4 folds, and validate on the remaining fold. This process is repeated 5 times, and each time using a different fold at the validation set. And finally, compute the average mean square error across all 5 folds to assess the model's performance. Now let's see how we can apply this theory in practice. And I will do this using Jupyter Notebook. I will show you an example of the most basic functions. But of course, in real life, things are much more complex. I think we can get to that a bit later. Why Jupyter Notebook? This tool provides an interactive environment where we can combine code, visual outputs, and explanation in one place. Then makes it easy to see not only the code itself, but also its results. This notebook format supports step-by-step exploration on the code. It allows us to run individual cells. In the first cell, we are using several important Python libraries. First of all, NumPy. is particularly useful for handling data preprocessing and performing numerical computations. Then pandas is used for data manipulation. We're working with data frames. Matplotlib is a plotting library for Python, which helps us visualize data by creating plots, charts, graphs, in order to understand the data better. Seaborn is built on top of Matplotlib and makes it easier to create attractive statistical visualizations. And of course, scikit-learn is one of the most widely used machine learning libraries in Python. Step 1, load a real regression dataset using the California house dataset from sklearn. For this, I use fetch California housing. Again, it's a real-world dataset for regression tasks. The next step, working with this dataset, we store the features in a data frame X and the target variable in an array Y. This dataset contains information such as median income, average house age, average number of rooms, and geographical features like latitude and longitude. Step 2, visualize the data. To better understand the relationship between the features and the target variable, we visualized the data using a pair plot from Seaborn. On the diagonal of the pair plot, we have density plot for each feature. And these plots show the distribution of each feature, giving us an insights into the spread, central tendency, and the overall shape of the data for each variable. If we observe uniform distribution in the correlation plots, it generally indicates that the variables are likely independent, or that their relationship is nonlinear, meaning one variable does not predictably influence the another in a straightforward manner. This is important when deciding which features might contribute effectively to our model. Step 3, splitting the dataset into a training and testing set using an 80-20 split. We then visualized the distribution of the target values in both sets using Seaborn's HIST plot. The plots show the target value distribution for the training set in blue and the test set in orange. This visualization helps us verify that both sets are representative of the overall data distribution, ensuring that the model can learn effectively from the training set and be evaluated fairly on the test set. Next, we train a simple linear regression using the linear regression class from scikit-learn. We use the training set X-train and Y-train to feed the model. And of course, we're using a model from a library, so we don't describe all the steps. We simply provide the necessary data as input. At first glance, this seems extremely simple, but without understanding how the algorithm works, we won't be able to build model effectively. After training, we used the test set X-test to predict the target value, YPRED. And finally, we evaluated the performance of the model using mean square error. In this example, the MCE on the test set was 0.56. which gives us an indication of how well our model is performing. And for a data set like the California housing data set, um, the MSE is generally reasonable, but not excellent. It indicates that the model captures some of the variability in the target, but there is still room for improvement. And depending on the context and the complexity of the data, further tuning or a more complex model might yield better result. And of course, the lower the MSE, the better our model's predictions align with the actual data. And to further evaluate the performance of our model, we plotted the actual values against the predicted value on the test set. The scatter plot showed the relationship between actual values on the x-axis and the predicted values on the y-axis, with the blue line representing the ideal scenario where predicted values perfectly match actual values. So in this plot, we can see a general trend where the predictions follow the actual values, but there is still a noticeable spread around the line. And this spread indicates that while the model has captured the general trend, it's not perfect, and some predictions deviate significantly from the actual values. Although we performed k-fold across validation using 5 folds, which means the data set was split into 5 parts. And the model was trained and tested 5 times, each time using a different fold as the test set and the remaining folds as a training set. As you can see, the average mean squared error across the fold was 0.56, and the bar plot visualization showed the MSE for each fold, giving us an insight into the variability of the model's performance across a different split of the data. And that's all for today. Maybe someone has questions, please. Okay, thank you so much for your attention.
Thank you also for such a nice lecture. So I hope we will continue next time, and we will have participants tomorrow. So please come tomorrow for our next lectures. And thank you all for participation.